Hello everyone, thank you for listening to this presentation. My name is Scher and I'll be presenting the work Warehouse Automation in a Day for Model to Implementation with Provable Guarantees. This work was done under the supervision of Professor Kress-Gazit in the Verifiable Robotics lab at Cornell. In this work we present a method for taking a model of a forklift or a robot or another vehicle for that matter, the blueprint of a warehouse and the high-level task of pallet deliveries, and automatically produce, without any special user expertise, the controls for the forklift, providing formal guarantees for completion and safety in an environment with dynamic obstacles such as humans and other robots, with some restrictions, as we'll see later. Material handling is a generic term that refers to any stage of the movement and storage of materials and products throughout the process of manufacturing, warehousing, distribution, and disposal. To make sure these supply chains work, the systems and equipment can be manual, semi-automated, or fully automated. In recent years, we have become even more reliant on online shopping and expect that the right package will arrive at our doorsteps on time. Even more so in these times of the pandemic, where the people wish to lower the risk of exposure. Human workers are very versatile, but a stressful environment and the sometimes daily routine tasks, like moving pallets with focus, for example, inevitably yields errors and high worker turnover, and also increasing the risk of injuries or being involved in accidents. Automated robots can join forces with the humans to reduce these errors and risks. We've probably all seen one of the videos from Amazon Robotics about how they operate a fleet of robots in harmony to deliver racks from place to place. In this case, warehouses are especially built for these robots, with all supporting infrastructure such as localization and the lack of unknown obstacles. An optimization technique assigns tasks to the robots, and if the warehouse changes and the optimization needs to be reconfigured. These robots are called AGVs, Automated Guided Vehicle. A guided vehicle follows fixed routes embedded in the ground. It is clever enough to use simple sensor in order to avoid hitting obstacles that come up in its way, but it's not clever enough to go around them and calculate a new route and work in an expanded environment without expanding the infrastructure, which is expensive and time-consuming. But what about pre-existing warehouses that are smaller than Amazon? What if they want to automate some part of the process while still having humans on the floor and want to be flexible with the automated tasks? This is the ballpark where we focus our work, and this is a good time to introduce the other paradigm, AMR, Autonomous Mobile Robots, which unlike AGVs are not restricted to fixed routes and can instead navigate dynamically using a map, allowing it to plan its path and travel quickly and efficiently throughout the environment. It can adjust to different environments more quickly and without the added expenses. In this figure, we show an overview of the whole system. We will dive into each part later. The inputs to our method are 1. The mathematical model of the robot could be kinematic, dynamic. 2. The environment settings. And 3. The task, a set of goal locations for the robot to visit. Once we have the inputs, we will construct a library of dynamically constrained motion primitives with funnels that correspond to all the possible locations the robot can end up in, given bounded disturbances and bounded controls. We then tile the motion primitives on the map, discarding motions that intersect with obstacles. We then take the constraints of the tiling and add the task requirements to create a specification in a formal language called linear temporal logic, LTL. There exist efficient tools to create controls from these specifications. This is called synthesis, such that we are guaranteed safe operation and task completion. We can then execute these controls on the real robot. Okay, so let's talk about the inputs. We could use any robot model for our method. We choose to use a car-like model called the Dubin's car. The reason is that it captures most of the dynamics of a forklift in low speeds, such as its non-holonomic nature. Also, the inputs linear velocity v and steering L of v are the common inputs for systems that come with their own low-level controllers. XY represents the position of the vehicle, and theta its rotation with respect to some fixed reference frame. The map captures the dimensions or bounds, the location of the fixed racks, and the rules of the road such as one-way aisles, keep to the right, and so on. The task comprises all of the goal locations, the do not enter zones, and the need to respond to any external events. We note here and explain later that this differentiation between the task and the map is somewhat artificial and can change. We differentiate the requirements that are pretty much fixed, the map, to those that can be changed more frequently, the task, by just resynthesizing a new control. The trade-off is between flexibility and compute times. Now we'll discuss about creating the motion library. The basis for this work comes mainly from two papers. In the first, the paper by Pivotoreco, a library of motion primitives are built with motions that are kinematically feasible. Then they discretize the problem by building a lattice of these motions, and the robot can then navigate from start to goal locations by searching for a path that does not intersect with an obstacle, such as the Dijkstra's algorithm. However, two problems exist. One, they assume the controller that can follow this path is available and exists, and this is not trivial, especially if the model is nonlinear. Second, what happens if the robot is subjected to disturbances or starts in a slightly different location or ends up in a slightly different location? The second paper by Majundo bridges these issues exactly. In this paper, they provide a technique to calculate low-level controls and the reachable sets where the robot can end up in while following a nominal trajectory for a nonlinear system subjected to bounded disturbances, bounded controls, and different initial conditions. Combining these two techniques together, we can harness the simplistic motion planning in the discrete space while having the funnels to ensure that we don't collide with obstacles under no circumstances, and also not worry about following the nominal path perfectly. In the procedure of creating these reachable sets, we first find a nominal dynamically feasible short path and obtain locally valid controllers. Then, using a procedure called sums of score programming, we obtain the funnels, all the states the robot could reach under a closed loop. In this figure, we see a cross-section of the motion primitives from the library. We choose to have diverse actions such as forward, backwards, passing, turning, and U-turns. We could add more versatility, but that would come with a cost of longer computation times. We start with an initial set that covers an entire cell, I'll explain that later, and propagate the reachable set throughout the trajectory until the terminal point. This means that if the robot starts in some cell, x, y, theta in our case, it is guaranteed to stay within that funnel, assuming our modeling assumptions are correct, of course. Now for the tiling. As we've seen, we compose funnels to create a graph, covering the entire free space. The graph is a directed edge-labeled graph. The vertices V are the cell centers once we uniformly discretize the configuration space, the states of the model. The edges are the funnels. For example, the motion primitive MPJ coming out of cell Ri and connecting to cell Rk exists and does not intersect an obstacle. We'll just mention that we use a library called FCL to check for intersections between the funnels and the obstacles. Specifications can be grouped into two main types. Safety specifications, which describe how the robot should always behave. This is what comes from the tiling. And liveness specifications, which describe what goals the robot might eventually achieve. Just before we go deeper, a short primer to linear temporal logic, semantics, and syntax to get acquainted with the symbols we're going to use. LTL is a mathematical language for describing linear time propositions. It contains Boolean operators such as not and or, and temporal operators such as next and until, that allows to reason about the change in the truth values of propositions over time. From these ones, we can also define more operators. Pi is an atomic proposition, a Boolean variable. LTL formulas are constructed from atomic propositions with this grammar. The semantics of an LTL formula, phi, can be defined over an infinite sequence of truth assignments to the atomic propositions. So, for example, when we say next phi, meaning that in the next step, phi must be true. When we say phi 1 until phi 2, meaning phi 1 is true until phi 2 becomes true. And when we say eventually phi, meaning at some point in the future, phi will be true. And always phi, meaning from this point on, phi is true for every step. One more important note. When considering multi-robot scenarios, global knowledge and centralized computation enable us a synchronized solution a priori and give formal guarantees. However, the computation times will be intractable, at least for real-world problems. Thus, we take a decentralized approach, only incorporate sensing of the robot's close vicinity and act upon that information, saying that if one of the funnels happens to be blocked, the policy should choose a different motion primitive to take. The inputs, the measurements of the environment, are the robot position. Ri is true if the robot is in cell Ri, and the blocked funnels at the current location. That could be sensed by LiDAR, camera, etc. The outputs are the motion primitives the robot decides to take. In this figure, when the robot is in this cell, the human will interfere taking a left turn, accounting for the robot size. So the policy outputs a forward motion. The key constraints and formulas from the specification are brought here. It is artificially divided into fixed and task parts to distinguish that to resynthesize a plan with only changing the goals is as easy as changing the goal locations and the initial conditions without having to retile anything. For the fixed part, first constraint comes from the tiling. It is how motion primitives move the robots between the cells. The second means that we cannot take a motion primitive that its corresponding funnel is blocked. The third just means that we can output a single command every step, and the last encode which cells do not have certain motion primitives. It will cause hitting an obstacle or drive the wrong way. Synthesis is about transforming a specification into an implementation. It is best viewed as a game between the robot and an adversarial environment. The environment chooses its next move in accordance to the specification, and the robot tries to react in a way that satisfies the specification. If it succeeds, it is called a realizable specification, and we can extract that policy as our control. If not, we need to change the task, the map, the motion primitives, etc. There's one more option to consider. We can have a specification that is reactive, with the blocked funnel sensors, and compute a priori all options and get provable guarantees. Or we can discard those variables from the specification and stop when we face an unknown obstacle and quickly recompute a new specification that disallows the travel to the blocked cells. Again, this is a compromise between faster computation times to having the guarantee that we can complete the task and acting faster in real time. Now we'll show some results. In this first demo, we have two robots in a reactive specification with no map restrictions. Robot 1 has 2 goal locations and Robot 2 has 3 goal locations. They start to move autonomously until they meet each other, plan a different action, and execute it. In this case, this robot takes a different action and because of that misses its goal point. It takes a different route, comes back around, and reaches it again. Even when an obstacle magically appears, the robot senses it, takes a different route, and continues on. The second demo is exactly the same settings, but the specification is non-reactive. This means we have to replan whenever we hit an obstacle. The robot senses an obstacle in its way, causing it to stop and generate a new specification. The robot will exclude the area occupied by the obstacle. Once done, in this case it takes about 10 seconds, it will continue on with its controls. The same happens in this case. In the third demo, we have two robots in a reactive scenario with map restrictions such as one-way aisles and do not enter zones. Just want to mention that no rubber duckies were hurt during most of the experiment. The robots drive autonomously with their policy until Robot 1 chooses an action that intersects Robot 2. In fact, none of the actions are valid in this case, so we add another stay-in-place action to the library until the robot can take a different one. At this point, this robot sees it cannot go back to reach its goal location here, so it needs to loop around to comply with the rules of the road. If a different obstacle is in the way, like when I prevented Robot 2 from taking a U-turn after reaching its goal, the robot reacts by choosing a reverse action and continuing on. With this, I want to end with a summary slide for your convenience and would like to thank you again for listening.